Good afternoon, everyone. We're going to go ahead and talk about the atomic structure now. We've taken the moment and we looked at who are the scientists that developed the models that helped us to understand the structure that we have. But now we need to put a little bit more information together and try to get it a current understanding of our actual atomic model and what are the pieces that make up that model. Learning goal: by the end of this video, you should be able to correctly identify the subatomic particles and their properties, explain what an isotope is and how it differs from a regular atom, and use the mass of the isotope in percent abundance to determine the average atomic mass for the element. So let's go ahead and get started. Starting off with our atom. Now, we said we use now the electron cloud model or the wave model. This model has a nucleus, which we have there in the center, which is made up of protons and neutrons, and the electrons around the outside. Still in the different energy levels, but again, not just scattered throughout, but they're actually arranged but moving all around at once. This table here is something you want to pause and make sure you have on your paper. Um, Subatomic particles, what are the names of them? Because I will use them a lot. The relative mass of each, the relative charge. Notice that it says +1, -1, or 0, and their location in the atom. A couple of these things I wanted to make sure they're there because I've had people in the past tell me all kinds of strange stuff. So starting off with the proton. Protons have a relative mass of about 1 atomic mass unit. That's what AMU stands for. A relative charge of +1. Necessarily we have the +1, and it's located inside the nucleus. Similar to this, we have the neutron, which has a similar relative mass of approximately 1 AMU, and this one actually has no charge. So that's why you have 0. Think neutrons are neutral. Now, these two are going to be located inside the nucleus to start with. Now, what about our third subatomic particle? That's going to be our electron. Now, notice that it's going to be very, 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 very small. Almost 1/2000th. 1 divided by almost 2,000. So extremely small. So it doesn't really factor into the mass too much. Has a charge of -1, and it's outside the nucleus. Still within the atom, but it's outside the nucleus. Some of these things in the next couple of slides will be things that you just need to remember. We talked about them before, and so you've had some experience. One, the atomic number. What actually defines the element? That's going to be the protons in the nucleus. For every atom of the same element, the number of protons is going to be the same. So for every hydrogen atom, we have 1 proton. For every helium, 2 protons, and so forth. The mass number is going to be made up of the sum of the number of protons and the number of neutrons in the atom. So this is actually going to change as we move into what we're talking about in terms of isotopes. But things to keep in mind here, since we said that our mass number, I'll write it in here, mass number equals protons, plus neutrons. If we are given our number of protons, we have our mass number, we can again always find our number of neutrons. Keep that in mind because we're going to need that a little bit later. Now, with each of these examples given here to the side, you notice I have lithium, lithium, lithium. The atomic number here, which we'll talk about in a second, is all going to be the same. But we have a different mass number. Why do we have a different mass number for each of these 3 isotopes, or 3 elements, atoms of lithium? It's because they are what we call isotopes of each other. Now, an isotope is an atom of the same element with a different number of neutrons. This is going to make it have a different mass. Here are a couple of examples that we're going to use. One for hydrogen. If you look over here, you notice that we have hydrogen with a with 1 as a mass number. We have hydrogen with 2 and hydrogen with 3. What's the difference? Well, the red dots represent our protons, and the green dots represent our neutrons. So, in what we call protium, or hydrogen with a mass number of 1, it's only 1 proton. But through other experiments and changes, we can end up with hydrogen 2, which is a proton and a neutron in the nucleus. This gives us a different mass to deal with. And again, tritium, which we have here, 1 proton but 2 neutrons available. This causes us to have a different mass, therefore a different isotope of the same element. Each time we still only have 1 proton. Similar thing for helium here. Now, some of you will probably look at this and say, okay, so what does this information mean? How do I read that symbol, that strange symbol? We talked about it a little bit before, but we're going to have here what's called a nuclide symbol or nuclear symbol. Nuclide. Now, in this nuclide symbol, you have the element symbol, which we talked about before, and then you have the mass number at the top. Usually it's actually going to be written on that side, and the atomic number on that side as well, on the other side as well. This is just to give us what the element is and to help us to figure out, which element and what the mass number and so forth are. Now, for a given element, there may be 5 isotopes, there may be 10 isotopes, there may be 30 isotopes. When we talk about those that are radioactive, you'll have many different isotopes of the same element because they'll begin to break down and lose those neutrons, which we'll talk about a little bit later in the same unit. But you want to keep these things in mind as we look at the symbols. That number up top is the mass number. Going back, that is our number of protons and neutrons. And we can find out the other information from there. Now, if I'm looking at my periodic table, if we're dealing with lithium, we pointed out the fact that I had these 3 different versions of lithium available. Mainly 2. Lithium 8 you don't really find so much, but we still keep it around, or we still keep the data for it. Now, when we look at this, at our periodic table, we see 6.941. But I have 3 different isotopes of lithium. How am I supposed to make that make any type of sense? How can I put that information together to get this single number? We're going to do what's called taking a weighted average here. So weighted average. You want to keep that in mind. This is a similar way to how we calculate your grades. Each of the categories is not necessarily represented or making up the same amount of your grade. So we can't just add everything up and then divide by the number of assignments or the number of grades. What we do instead is we take what's called a weighted average, which takes into account the percentage of each of it, or each percentage or area of your grade. Now, in the case of what we have here, 92.5% of the time, we're going to run into lithium 7, with only 7.5% of the time running into lithium 6. The other one, like I said, is very rare, less than 1%. So how do I come up with 6.941 from the 92.5% lithium 7 and 7.5 lithium 6? Glad you asked. What we're going to do is we're going to take into account both of these pieces of information and multiply and add them up to get our final total, or get something near our final total. So, taking our information, we're going to take this 92.5 and turn it into a decimal, 0.925, same as just dividing it by 100, and do the same thing here, 0.075. This allows us to be able to actually multiply without running into any issues. Now, let's go back. Now, we're going to take this percentage, this number, this decimal that we're dealing with, and multiply it by the mass we were given. Since I wasn't given any other special numbers, I'm just going to use the 7 that was given to me here. 7 and 6. So 0.925 times 7 plus 0.075 times 6. Getting that information, now all I have to do is add it up and I get 6.925, which is not far from my original answer and would be within the acceptable range of error. But this is how we would go about calculating what's called the average atomic mass. Sorry, bug flew in my face. This is again the average atomic mass. Let's go ahead and get that fixed. There we go. And we're going to use this information throughout the rest of this unit. And as we lead into the other portions of the unit, of course, where we'll get deeper into this part. But stay tuned because we have a little lab that we're going to do with this. It's kind of sweet, really sweet. I enjoy it. Well, that's where we're going to actually end this portion, this section for today. Have a great afternoon and look forward to seeing you in class.